and preservatives. I've labeled this as Part B of Chapter 7, but it's really not actually talked about in Chapter 7, but it goes with that chapter in the sense that we're talking about control of microbial growth. We usually talk about these in the lab, but I wanted to make a few points because antibiotics and preservatives are actually very important in our daily lives. The antibiotics we're just going to cover briefly, but if you're looking for some background information, it is found in Chapter 20. However, the preservatives is just information that I have found from various places, so there's no real reference for that. When we talk about antibiotics, the first antibiotic was penicillin. Penicillin was discovered in 1928 by Fleming, who actually a couple of years before had found that the lysozyme in our secretions in tears actually was antimicrobial as well. So he kind of discovered the penicillin by accident in that he was working with bacteria, but in a microbiology department, there were other people that were working with fungi. And he noticed that whenever he got a colony of penicillium on his plate, he had an area of inhibition where his bacteria didn't grow. And so he started to think about what compound was being made by this penicillium fungi. So they were able to determine the compound, and this was then put out as what we now refer to as penicillin. In 1940, Howard and Florey and Ernest Chain actually performed the first clinical trials of penicillin. When penicillin was first put out on the market, this was supposed to be the miracle drug because, again, penicillin is attacking the cell wall. The peptidoglycan cell wall is unique to bacteria, so people thought this was going to be our answer to all of the plethora of bacterial infections that we faced. Unfortunately, we learned very quickly that penicillin isn't the wonder drug. It's still used today, which is rather surprising. However, it's not going to be the wonder drug we had hoped, for the fact that many bacteria can actually inactivate penicillin and so therefore are resistant. We start to see, though, in general, that we're having kind of a reality about the use of antibiotics. We rely heavily on antibiotics. The antibiotic market is over $3 billion worldwide. But truly, the antibiotic pipeline is as empty as it has been since the discovery of antibiotics. So we started with the one, penicillin, is like, oh, this is going to do it all. And we really haven't gotten that much better. That's because 97% of antibiotics in development are actually analogs of things that already existed. We're not really developing a lot of new ones. And the antibiotic resistance has emerged as a major challenge in public health and personal health. The World Health Organization has made this one of an urgent need to find new antimicrobials. So that's why we really start to have to question the search for what has been termed that single blockbuster broad-spectrum antibiotic, both from the standpoint of medically and ecologically. People have been looking for these in places like the rainforest and things and saying, all right, if we just go looking, we're going to find things. But should we just be putting all this emphasis into discovery of antibiotics when the microbes just seem to get around it in the first place? However, the reality, we rely heavily on antibiotics, and the antibiotic resistance is a major issue, but it's the tools that we have. When we start to talk about new antibiotics, people always are trying to look for these new sources of where we can find them. So places scientists are looking are sometimes unusual. These fungus-forming leafcutter ants, they actually make antibacterial peptides because they need the fungus that they use to pack in their nest to be able to digest the leaves that they bring back. And they don't want that fungus farm to become contaminated with bacteria. And so we're finding unique potential antibiotics from them. We've found things from places like the Atacama Desert in Chile, marine sediments, marine sponges, even common garden soils. We actually have a class called Discovering Antibiotics, where we have students go up and dig up the soil and look for antibiotic-producing microbes. Golf courses. The ivermectin was actually found on a golf course in Japan, and weirdly, other sources. Cats' noses have given us some interesting organisms that are fairly antimicrobial. And the weirdest one is men's beard. Men's beard have a lot of microbes there. And when they did a study of about 100 bacteria isolates taken from 20 different beards, they found about 25% of these actually showed antibiotic activity against indicator strains that were tested. So people keep looking at these unusual places to try to find the next new antibiotic. But again, the cautionary tale is that the next blockbuster just might not be out there. That being said, we do a lot with antibiotics. By definition, an antibiotic is a substance produced by a microbe that, in small amounts, inhibits other microbes. We've kind of taken that true definition and expanded it. There are only a handful of truly synthetic antibiotics. We do see, however, that many of these are now semi-synthetic. So again, you start with the one that you've isolated from an original microbe and then modified it to improve it so it starts to become semi-synthetic. When we think of representative sources of antibiotics, things like Bacillus have given us the bacitracin that I'm sure you've heard of. Streptomyces has been a very fruitful genus, so things like streptomycin and amphotericin B. And the fungi, not only penicillium, but a number of fungi are antibiotic producing. The action of antimicrobials, we said in the previous part A that things can be bacteriostatic, which prevent microbes from growing, or bactericidal, actually killing the microbes. Not only is that true for our disinfectants that we were thinking about, but it's also true for antibiotics as well. So you see things like chloramphenicol, erythromycin, tetracyclines are actually bacteriostatic, whereas things like our big guns, aminoglycosides and vancomycin, the metronidazole, these are all bactericidal. But the same thing that is true in general when we develop any drug, even for these antimicrobial drugs and antibiotics, we have to develop things that have selective toxicity. So that's why people got excited about penicillin. It was going to kill microbes because it was attacking the peptidoglycan that only the microbes had. So we want to think of ways that we're going to do harm to the microbes without damaging our own eukaryotic host cells. The other issue that we're facing are superinfections. When we use these antimicrobial drugs, antibiotics, they don't know the difference between good and bad bacteria. So yeah, they're going to kill the pathogen, but the problem is that they're also killing normal flora as well. So if you kill the good normal flora, that means you often get an overgrowth of an opportunistic pathogen that was being previously kept in check, and now you have this overproliferation, this superinfection. As noted previously, we're having a lot of issue with antibiotic resistance. When we talk about how an organism becomes resistant to antibiotic, it's a selective process. We said bacteria grow by population, not individual cell size. So therefore, when you have population of bacteria, you have a lot of bacteria. And they undergo mutation rate quicker than other organisms, much quicker than our own eukaryotic cells. So therefore, just by chance, some of them are going to end up having resistance. And therefore, if they then get exposed to that antibiotic, The antibiotic kills all those bacteria that are sensitive. However, they then leave the ones that are resistant. Again, that antibiotic treatment is not only killing the pathogen that you're trying to kill, but it's also killing good bacteria that now you've only got these resistant strains, and they could potentially make opportunistic pathogens. So the resistant bacteria now have the preferred conditions and overgrow, and that's when you start to have populations of antibiotic-resistant bacteria. Even more problematic is that the bacteria can transfer their drugs resistance to their neighbors. So whether it be by their pili or other things, they can actually, once one has it, transfer it to their neighbor. And that's why antibiotic resistance is becoming such a global crisis, one that the World Health Organization said that this could truly undo many of the advances that we have made in modern medicine in controlling infections. When we talk about the ability for these antibiotics to kill either a wide range of microbes or a narrow range, we're usually referring to whether they kill both gram-positives and gram-negatives or just one or the other. A broad-spectrum antibiotic is going to be effective against both gram-positives and gram-negative bacteria. We don't want to start having organisms resistant to these broad-spectrum antibiotics because then we're not going to have the ability to treat, and therefore clinically we want to use narrow spectrum when possible. We just need to be mindful about the spread of antibiotic resistance. So if we look at the table from chapter 20, we see things like penicillin is going to be most effective against bacteria against gram-positive bacteria because they have the peptidoglycan cell wall. Something like streptomycin is effective against gram-negatives and the mycobacteria, so a little bit more wide range, but a true broad spectrum is something like tetracycline. It's effective against gram-negatives and gram-positives, and actually some of the mycobacteria and chlamydia and rickettsia as well. The eukaryotes are going to have their own they're not truly antibiotics, but their own antifungals or antiprotozoals or the other antiviral types of things like acyclovir. So we really do look at things for those that are going to be against prokaryote and those that are going to be against eukaryotes are separate categories of antimicrobial drugs. For the antibiotics and prokaryotes, where do we want to hit them? The major modes of action are going to be, first, probably target the cell wall. The peptidoglycan cell wall is going to be unique to the prokaryote, so that's why you see a number of things like penicillins and vancomycin targeting there. Next, inhibition of protein synthesis, things like chloramphenicol and tetracyclines. That's because the ribosomes that are the site of protein synthesis vary in a prokaryote and a eukaryote. Those are by far going to be the most likely points of action that we're going to try to kill the bacteria. We can also do things like inhibit nucleic acid replication. These are the big guns, the quinolones and the rifampin. However, DNA is universal, and so therefore doing this in a microbe can potentially harm host cells as well. Injury to the membrane, we only do this topically with things like polymyxin B. That's because, again, the membranes that eukaryotes have are similar to the membranes of prokaryotes, therefore it's not a very selective target. Every once in a while, we get lucky and find an enzyme that we can inhibit as an essential metabolite. The example, the sulfa drugs. So we can prevent the production by cells, bacterial cells of folic acid, inhibit their ability to make their DNA. But we don't have too many examples of that type of target. If we take a look at some specific examples that you, I'm sure, have heard of, vancomycin was named such because it was going to vanquish those pesky bacteria. This is a polypeptide antibiotic that is most effective against gram-positives. It was discovered in the 1950s, and this was supposed to be the alternative to treat penicillin-resistant, especially the staphylococci. So we got really excited about this, and it is still effective, but we are starting to see some resistance even to vancomycin. This has become especially problematic because of the emergence of our MRSAs. MRSA stands for methicillin-resistant Staph aureus. These started to develop in the 1980s. Methicillin was again supposed to be an alternative to penicillin. We quickly saw the evolution of our MRSA strains. Vancomycin is considered the last line of defense against these MRSAs. And now that we're starting to see these VRSAs and also vancomycin-resistant enterococci, we really are concerned that we may be facing a medical emergency where we're going to find it problematic in hospital settings to be able to treat these type of resistant, especially Staph aureus, because we just do not have other alternatives. The vancomycin specifically is working at the cell wall, not looking at the backbone, the NAM and NAG linkages, but those tetrapeptide chains that we talked about that allows for a thick cell wall of peptidoglycan to be stacked on top of each other. It kind of caps off those peptide side chains so that the cell wall becomes unstable. It also has a little bit of effect on the membrane, the cell membrane as well. So it's a very effective antibiotic. Tetracycline, on the other hand, things like tetracycline is they're a broad spectrum antibiotic that inhibits protein synthesis. It interferes with where the transfer RNA attaches at the ribosome during protein synthesis, and therefore it's effective not only against gram-positives and gram-negatives, but also chlamydias and rickettsias. We haven't talked about them yet, but they are clinically relevant. If as a child you happen to have been given a lot of tetracycline, maybe you had chronic ear infections or something, this usually interferes with the deposition of enamel, and these children often ended up with discoloration of their teeth, and therefore we want to be careful about making this a common use antibiotic. It is only bacteriostatic, as we said before, so that means that it's inhibiting but doesn't actually kill. One of the biggest problems that we're having is the overuse of tetracycline, especially in animal feeds. The little figure there of who's hogging our antibiotics points to the problem that up to 70% of the antibiotics in the United States actually go to farm animals that aren't sick. We're constantly trying to prevent them from getting bacterial diseases, especially because of the way we rear them in very crowded conditions. However, this is just contributing to antibiotic resistance against this broad spectrum antibiotic, and that's problematic. We see here tetracycline, as I said, is going to interfere with the attachment of the transfer RNA to the messenger RNA ribosome complex, and this is only going to be for a prokaryotic ribosome. Remember, a prokaryotic ribosome is the 70S variety. Eukaryotes have the 80S variety, so these drugs are selective in that they're only going to affect the prokaryotic ribosome. There are other things like chloramphenicol and streptomycin that as well inhibit protein synthesis, but by different mechanisms. The injury to the plasma membrane, not a common target, but we see things like polymyxin B is bactericidal when it is used. It is used for topical use only. That's because, as I said, our membranes, bacterial membranes, that phospholipid bilayer is similar in most organisms, and therefore it would do potential harm to the eukaryotic host. We see polymyxin B commonly combined with bacitracin and neomycin in the over-the-counter, the tri-antibiotics that we buy to put on wounds and cuts and scratches. It's very effective, but again, we want to make sure that we're not overusing this so that we don't have problems with antibiotic resistance. The unusual category of the sulfa drugs, initially, these were ones that are commonly used because sulfa drugs are very effective. That is because their mode of action is as inhibitors of nucleic acid synthesis by inhibiting essential metabolites. When we talk about the sulfa drugs, though, a lot of people are actually allergic to them, so it's a little bit hit or miss of who can use them. They are bacteriostatic, and different forms of sulfa drugs will inhibit different enzymes in the pathway that is needed to create our purines, and those purines then are used to make our DNA. So we see that things that are analogs to the para-aminobenzoic acid are going to interfere with that and inhibit the enzyme that is going to give rise to our dihydric folic acid. Then the trimethoprim is going to inhibit the next one that leads to making of the tetrahydrofolic acid. And if you use them in combination, you actually get a nice synergistic effect. But in general, these are going to be used to inhibit the synthesis of DNA by that bacteria. As we said in the previous slideshow, the easiest way to look at this in the lab is doing that disk diffusion test. So we did that with the antibiotics, we did that with the disinfectants, where we just put the disinfectant on a filter disc and dipped it in there and put it on a lawn of bacteria. Well, we buy commercially antibiotic discs that already have a prescribed amount of the antibiotic incorporated into that filter disc. We just put that on our lawn of bacteria and look for our zones of inhibition. Plating out a lawn of bacteria, if we were doing lab this term, we would have plated out our lawns, applied our disc, and then incubated at 37 degrees and then measured our zones. What you're looking for is the MIC, the very edge where that zone of inhibition stops and the growth begins. That means that's the minimal inhibitory concentration. The antibiotic is diffusing away from the disc, and as it diffuses out, it's becoming more dilute or less concentrated. So the minimal inhibitory concentration is the concentration that is now too dilute to kill the bacteria. So that's why you get that distinct ring around the zone of inhibition. We can also call this the minimal bactericidal concentration, again, if we're working with something that's specifically bactericidal. So normally what we do is we measure these, and then for antibiotics, we have a table of the zone of diameters for various known organisms as interpretive standards, and we can then evaluate the antibiotic. You usually use what's referred to as Mueller-Hinton agar as the medium of choice. It's softer and has fewer nutrients, so it doesn't inhibit the spread of the antibiotic, and it's also just going to be easier for it to diffuse to be able to get good zones of inhibition. Besides antibiotics, there's also preservatives. Preservatives are both naturally occurring or synthetic. When you say preservatives, people kind of go back and forth. Some people automatically think, oh, those are natural, right? And others right away start saying, oh no, it's the artificial preservatives. But anything that is able to prevent microbial growth can be considered a preservative. And these are things that we add to food, pharmaceuticals, and even things like paints and various things. We see commonly food preservatives are based on some things that are synthetic, other things that are natural, like our spices and acids. But we put a lot of things in cosmetics, which is a little bit more controversial. People do ask, does that cosmetic need to have that protection against bacteria and fungi? Well, probably yeah, because you're constantly handling it and you don't want to be contaminating things that could potentially be put in your pores or eye makeup, things that could potentially cause infection. But it is a true statement. We do tend to overuse these types of substances in foods and our cosmetic industry. However, we do need them. If we think about some of the common preservatives, if you read your labels, propionic acid inhibits the growth of molds and some bacteria, Fortunately, these can be used in very small amounts, and that's why they're good for incorporating into foods. They're not going to allow a large change to the taste because you're not incorporating a large amount. Propionic acid, people usually think of this as those artificial preservatives that they don't want in their food, but it actually occurs naturally in apples, strawberries, tea, and violet leaves. And so it has been used as a common inhibitor and in preservative, especially to prevent mold in baked goods and processed cheeses. But we also see it in butters and ice creams and candies. Again, used in animal feeds to prevent mold growth on stored grains. But that is part of the problem and the dichotomy. We need it for shelf life of our foods, but if we don't use it on some of the things that we feed our animals, then they could potentially be eating contaminated foods as well. So we definitely end up having a little bit of a circular argument there. And that's why we see that these are incorporated into hay, drinking water for our poultry and livestock to try to prevent infection from their foods as well. Sorbic acid is one of the most common. If you look at the products pictured in the corner, we see that this antimicrobial is found in so many things. Anything from cheeses and yogurts and prepared salads and soft drinks and pickles, you name it, it probably has sorbic acid in it if you read the label. It's usually used as a salt form, sodium sorbate, potassium sorbate, or calcium sorbate. As the sorbates, again, you can use very low concentrations, so that way you're not adding a lot of this to be able to incorporate it into the foods. It does occur as a natural compound, but is mostly made synthetically at this point, which is why people think of it as the artificial preservative. But it was first isolated from berries in the 1800s and became one of the first commercially available food preservatives in the late 1940s. So people are always saying, we don't want preservatives in our food. No artificial preservatives? What happens? I couldn't help but be intrigued when I saw this. So Burger King put out an ad campaign with this moldy burger. And one of the articles that I looked at was, Burger King hopes your hatred of preservatives is more powerful than your hatred of moldy-ass food. It's like, all right, I'm intrigued. Well, apparently the Burger King has been advertising that they are removing artificial preservatives and colors and various flavors from their Whoppers. They have said that they will do this in all their U.S. restaurants by the end of the year, and this was announced in February of this year, so February 2020. And they are removing artificial additives from their Whoppers in about 400 restaurants already, and most of their European franchises. And so therefore, you kind of think about this and go, all right, well, you're removing the preservative, but you're showing me a moldy burger. They actually have a video of a Whopper that is left to rot over the course of 34 days. So this is the 34-day picture where you have this gross, just thick fungal mold growing. And the tagline is, the beauty of no artificial preservatives. And you're looking at this and going, what are you talking about? Well, this is actually them taking a shot at their rival, McDonald's. McDonald's has actually long been plagued by a stunt where people have claimed that they have so many preservatives in their food that it lasts forever. So there's actually a famous burger and fries that were purchased from the last McDonald's in Iceland before it closed. And that was back in 2009, and it's still going strong and looks fine. And so the idea here is that they're proposing that McDonald's has put all these preservatives and colorings and other artificial additives in there, and that the Whopper is better because it doesn't contain these artificial preservatives. A Whopper, you can get away with no artificial preservatives, This is food that is meant to be prepared right away and then eaten. So you don't expect that something is going to be around for 34 days unless you put the Whopper to the back of your refrigerator or your backpack or something and forgot about it. But in general, you're going to eat that as soon as it's made. We still do have issues of temperature abuse, and we'll talk about that in our GI chapter for all of our foods. But long term, yeah, you don't probably need those preservatives for something like a Whopper. However, why do we need preservatives? The simple answer is shelf life. We no longer live on the farm, and therefore when we have food, as I said previously about pasteurization, things have to go from farm to store to table and all the transport in between. So people need longer shelf lives, and that's why preservatives are keeping our foods safe and fresh for longer periods of time, because we want the convenience of being able to grocery shop rather than going to the farm to get our food. That doesn't mean that everything when you say a preservative is the artificial variety. Natural preservatives are also being used and are actually making a comeback. These have been the preservatives that have been found in foods since the beginning of people making food. When we talk about things like black pepper, it has an active ingredient that is going to be both an antimicrobial against bacteria and an antifungal. Pepper is used worldwide, and it has the potential to actually now be helping to not have to use so many antibiotics. As new antibiotic-resistant foodborne pathogens emerge, going back to some of these natural preservatives might be the answer. We also see cloves. Cloves have an active ingredient, the eugenol, that is going to, again, have very potent antimicrobial properties and seems to be effective against a number of our known foodborne pathogens. It's also an antioxidant, which is good. In its dried variety, it basically has also been used as a flavoring, and therefore getting back to some of these naturals is an important antimicrobial and could help in our fight against the numerous emerging foodborne pathogens. Other things that you're familiar with? Mustard. This antimicrobial is also aided by the fact that it's an antibiotic-producing activity as well. It's effective against a number of foodborne pathogens and a common ingredient and condiment for foods. The problem, the amount. How much are you putting in? And so when we talk about these other preservatives, those artificial ones, we're measuring to make sure that there is an effective amount. Now, when you have something natural, yes, it can do the inhibition. However, how much is there? You're changing the flavor, and therefore the use of these natural preservatives may be a little bit more tricky, but definitely something we want to explore. Cinnamon is another broad spectrum. It as well seems to help strengthen the immune system and is effective against fungi, viruses, and bacteria, and just tastes good. That's why it's a common spice in many of our baking recipes. So natural preservatives, are they good? Absolutely. Are they effective? Probably. A combination of garlic and clove is able to kill 99% of E. coli in salami. Remember, though, that salami may be aided by the fact that we talked previously about these things being fermentation products and how that is also important in helping to preserve some of these foods. But the point is that we can be looking at some of these natural preservatives for some of our answers, but that's not to say that the artificial preservatives are not still going to be needed. And as well, just because we're making them synthetically, many of them did come from natural sources, and we do have to remember the purpose. Without it, we would not have the shelf lives that we need for many of our food products, and that would be problematic from the standpoint of many of our emerging foodborne pathogens. So for the preservatives in the lab, we can measure them as well. Typically, we actually take the powder or liquid form of the preservative and directly incorporate that into the agar plates. If we were doing this up in lab, we would have then just streaked a single line of inoculation onto the plate and see if the microbe grew or not. I like when we make our clove plates because the lab actually smells really good. You could also do a serial dilution if what you have of the preservative is in a liquid form. So you could dilute that and then put the different dilutions, spot those on the plate, and you could then actually see whether you had antimicrobial activity in that way as well. So preservatives, we need them. They are a great way to help us prolong the shelf life of our food. And again, preservatives along with antibiotics are oftentimes what keep us safe from a plethora of foodborne pathogens. But with the antibiotics as well, we're treating a lot of other infectious diseases that we will talk about later in the term.